Welcome back. In today's class, we will start with Module 4. Module 4 is hydraulic turbines. So as the name indicates, here we will be dealing only with turbines where the working fluid is water. In the elements of mechanical engineering, I think you have studied about Pelton wheel, Francis turbine, Kaplan turbine. So these are some of the examples for hydraulic turbine where water is used as the working fluid, and based on the head available and several other factors such as the flow rate available, so we decide the type of turbine. So in today's class, I will cover the classification, different heads and efficiencies, and then the construction and working of Pelton wheel. So before going to that, first let us see or recall about the hydraulic turbines. So to produce energy with the help of an hydraulic turbine, we need to store water at a certain height. For that, we need to construct a dam. So here we have a dam and the water will be collected behind the dam. So the water level in the dam, we call it as headrace level, and then the water will be supplied to the powerhouse, which is the place or the room where we keep the turbine generator set. So depending on the amount of water available, we can have only one turbine generator set, or we can have multiple number of turbine generator set. Okay. The water from the dam will be carried to the powerhouse through a pipe called as penstock. So again the size of the penstock depends on the amount of water flowing through it or the discharge available throughout the year, and depending on the size, we decide to use a metal pipe or a concrete pipe, or if there are any obstructions, maybe there is a mountain in between the dam and the powerhouse, then we can also have tunnels through which the water flows. And very close to the powerhouse, we will have the surge tank, which is provided as a measure to absorb the impact of water when we suddenly close the valve, or when we close the valve, we have an effect called water hammer effect, and to absorb the pressure rise that occurs during the water hammer effect, we will have the surge tank either near the dam or near the powerhouse. And then the water from the powerhouse enters the tail race. It is a small pond kind of a structure where the water from the powerhouse, after passing through the turbine, will enter, and from here it will be redirected back to the river. This is the basic working of a hydroelectric power plant, and here the head available for power production is the difference between the head race level and the tail race level. So this head, we call it as capital H. So the total head available, we call it as gross head Hg, but out of that, as the water passes through the pipe, there will be some losses due to friction or the fluid friction, and that loss I will call it as Hf. So the net head available for production will be capital H, which is capital Hg minus Hf, that is the losses or the friction component of the penstock. So this is the head available for power production, and if you remember, in fluid mechanics we have studied that the power transferred by a fluid to a solid surface will be given by rho q gh, where h is the head, that is the net head, and q is the discharge through the penstock. So rho is the density of water, rho into q into g, that is acceleration due to gravity, multiplied by the net head, will give us the power available, or the power that can be converted into mechanical energy or mechanical power in the powerhouse. Now let us see the classification. So the classification are made under different headings. The first heading is based on the action of water on blades. So when the jet of water or water impinges or impacts the blade, Depending on what kind of energy is absorbed by the blade, we have different classification. The first one is impulse hydraulic turbine or impulse turbine. In this case, we all know that if we are talking about an impulse turbine, then the energy exchange occurs only due to the kinetic energy. So, in the case of an impulse turbine, when the water comes from the dam to the powerhouse, at the entrance to the turbine there will be a nozzle, and that nozzle converts all the pressure energy. So, as the water passes through the penstock, it will have certain amount of pressure energy because we are storing water at a certain height. So, it will have certain amount of hydrostatic pressure or potential energy, and all that will be converted into kinetic energy. So, that increases the velocity of water. So, when the water strikes the blades of the turbine, only the kinetic energy of the water will be absorbed. Then those kind of turbines we call it as impulse turbine. So, here only kinetic energy will be absorbed, or only kinetic energy of the water will be converted into mechanical energy. So, those turbines we call them as impulse turbine, and the best example for that is Pelton turbine or Pelton wheel. So, Pelton turbine or Pelton wheel is an impulse hydraulic turbine. Then we have the reaction turbine. So, in the case of reaction turbine, there will be changes in the kinetic energy as well as pressure energy as the water flows through the turbine. So, the blade or the runner absorbs a part of kinetic energy and a part of pressure energy. So, because of that, because of the change in pressure energy, there will be a reaction force, and hence the name is given as reaction turbine. In the case of a pure reaction turbine, there will be no changes in the kinetic energy of the fluid, and the energy exchange that happens will be only due to change in the pressure. So, due to change in pressure, there will be reaction force, and those kind of turbines we call them as pure reaction turbines. But in practical cases, we do not have any pure reaction turbine. Whatever we have is a combination of impulse and reaction turbine. Hence, here the kinetic energy as well as pressure energy will be converted into mechanical energy. So, we do not have a pure reaction turbine. All the reaction turbines which we encounter in our day-to-day life or in our engineering, all are impulse reaction turbines, but we call them simply as reaction turbine. And to give us an idea of how much energy is being converted or how much pressure energy is being converted and how much kinetic energy is being converted into mechanical work in a given impulse reaction turbine, we have a term called degree of reaction. If it is very close to 1, it means to say that a larger amount of energy is being converted is pressure energy. If it is close to 0, then a large amount of energy which is being converted from fluid energy to mechanical energy will be in the form of kinetic energy. For an impulse turbine, the degree of reaction is 0. For a pure reaction turbine, the degree of reaction is 1. So, the value of degree of reaction varies from 0 to 1. Okay. And the best example for a reaction turbine is a Francis turbine, Kaplan turbine, propeller turbine. All these are examples for a reaction turbine. Next classification is based on the direction of flow of water through the runner or through the turbine blades. And here we have several classifications. The first one is tangential flow turbine. The first one is tangential flow turbine. In this case, here we have the runner and then we have the shaft. So, the water will be flowing tangential to the runner. So, here the water is flowing tangential to the runner. So, these kind of turbines we call them as tangential flow hydraulic turbines, and the example for this is Pelton turbine or Pelton wheel. Then we have radial flow turbine where the flow will be always radially inward. So if the flow is radially inward, then it becomes a power producing turbo machine. If the flow is radially outward, as in the case of our centrifugal pumps, it becomes a power absorbing turbo machine. So if the flow is radially inward, so this is the shaft is perpendicular to the board, and if the flow is flowing radially inward, then those kind of machines we call them as radial flow turbines, and the best example is Francis turbine. And then we have the mixed or diagonal flow turbines. So as the name indicates, here the flow will be radial as well as axial for the shaft. So these kind of turbines we call them as mixed or diagonal flow turbines. And here you can see that this is a modern Francis turbine where the water enters radially inwards and leaves axially. So this is the shaft, the water is leaving parallel to the shaft, then we call them as axial flow, and it is entering into the center, the water is flowing towards the center of the shaft, that becomes the radial flow. So we have radial at the inlet and axial at the outlet. So these kind of flow we call them as mixed or diagonal flow turbines. So the best example is modern Francis turbine. Then we have axial flow turbines. So in the case of axial flow turbines, the flow of water will be parallel to the shaft when the water is flowing through or when the water is flowing over the runner or the turbine blade. Here you have the couple-on turbine, and here you can see that we have the blades here and the water is flowing through the blades parallel to the axis. So this is the shaft and we have the axis in the vertical direction and the water is flowing parallel to the shaft or the axis. So hence it is called axial flow turbine, and the best example here is couple-on turbine or propeller turbine. Okay. Then we have the classification based on the specific speed. So based on the specific speed, if you remember, the speed of a turbine which is producing unit power when working under a unit head and unit discharge. So in that case, so we have low specific speed turbines where the head available for the turbine will be around 200 to 1700 meters. So they are very high head turbines, but the discharge in this case will be very low. So because of that, since the head comes in the new denominator of the specific speed, so they will have very low specific speed. For a Pelton wheel or a Pelton turbine, for a single jet Pelton wheel it is around 10 to 50. If you have two jet, then it ranges from around 35 to 60. But the specific speed for the Pelton wheel will be always very less. That is because the head is very high and the discharge is low. So because of that, the specific speed will be very low for a Pelton wheel. So this is classified as a low specific speed turbine. Then we have medium specific speed turbine where the specific speed ranges from 60 to around 400. So in this case, we have a head of around 50 meters to 200 meters, which we call them as medium head turbines, and the discharge of water will also be medium in this case. So because of that, we get a medium range of specific speed, that is around 60 to 400, and in this case the example is a Francis turbine. Then we have high specific speed turbines where the head available is very less and the discharge is very high. So because of head being very less, that is around 2.5 to 50 meters, so they are called low head turbines. But at the same time, since head is very less, the denominator of the specific speed is very less. Because of that, the specific speed value will be very high, and here it will be in the range of around 300 to 1000 specific speed. So here the example is couple-on turbine or propeller turbine. These are the examples as well as the classification of hydraulic turbine. Now let us see the different heads as well as efficiencies involved in a hydraulic turbine. So the hydraulic heads are, first one is the gross head, and as I said in the beginning, that is the difference between the head level of the head race and the tail race. So that is the height difference between the head race and the tail race, and it is denoted by the letter HS or HG. In some of the books they denote it as HS, and in some of the books it is denoted as HS. Then we have the net head or the effective head, and that is the head available for the power production at the inlet of the turbine. That is, after removing the losses, after taking out the losses, whatever the head available in the gross head, that we call it as the net head or the effective head, and that is denoted by capital H, and that is given by Hg minus Hf, where Hf is the losses that occurs due to friction as the water flows through the penstock. Then let us see the efficiencies. So we have the hydraulic efficiency eta H, which is the ratio of power developed by the runner to the power available at the inlet. So as I said, power available at the inlet will be equal to rho q gh or mgh, m dot gh. Rho into q gives us the mass flow rate. So mass flow rate into g into h, or rho into q into g into h will give us the power available at the inlet, and the power developed by the runner will be given by the Euler's equation, which is m dot, that is the mass flow rate of water, into Vu1 U1 plus or minus Vu2 U2, or it can be written as He divided by H, where He is the Euler's head, because at the top we have the power produced given by the Euler's equation, and denominator it can be written as the head. So in terms of head, it is He minus H, or it can also be written as head available minus head losses divided by head available. So that gives us the hydraulic efficiency, or how effectively the turbine has converted the energy available in the water into theoretical work. Then we have the volumetric efficiency denoted as eta vol. So here it is the ratio of the actual quantity of water striking the runner to the quantity of water supplied to the runner. In a turbine, all the water which enters the turbine will not strike the runner blade, and there will be some slippages. So we need to consider that while calculating the power output. So if the slippages are more, then the amount of energy produced will be less. So volumetric efficiency is also a very important parameter, which gives us the ratio of actual quantity of water striking the runner to the total amount of water supplied to the runner, and that can be mathematically written as QA divided by Q theoretical, or where QA will be equal to Q theoretical minus the amount of water which slips through the runner blades, that is delta Q. So it is Q minus delta Q divided by Q, that is volumetric efficiency. Then we have the mechanical efficiency eta mech, and the mechanical efficiency is given by the shaft power output divided by the power developed by the runner, that is the theoretical power developed by the runner. And we have seen that the theoretical power developed will be m dot into Vu1 U1 plus or minus Vu2 U2. So the mechanical efficiency will be equal to shaft power, that is Sp divided by m dot into Vu1 U1 minus plus or minus Vu2 U2. Then we have the overall efficiency, which is the product of all these efficiencies. Our overall efficiency is the ratio of shaft power output divided by the energy available at the inlet of the runner, or the fluid power available at the inlet of the runner, and that is given by rho q gh. The fluid power is rho q gh, and the shaft power I will represent it as Sp. So it is Sp divided by rho q gh. So rho into q is also equal to m dot, or you can write it as m dot into gh. So the overall efficiency can be written as product of hydraulic efficiency, volumetric efficiency, and mechanical efficiency, or it can be written as actual hydraulic efficiency multiplied by mechanical efficiency, where actual hydraulic efficiency is the product of volumetric efficiency and the hydraulic efficiency. So these are the different efficiencies and heads which we encounter in a hydraulic turbine. So here we have the diagram of the Pelton wheel. We know that a Pelton wheel is a tangential flow impulse turbine. So it's a tangential flow impulse turbine because the water will be flowing tangential to the runner. So here we have the runner, then we have the shaft. The runner is mounted on the shaft, and over the runner we have mounted the buckets. So these are the buckets which absorbs kinetic energy of water and converts that into mechanical energy. Here we have the water jet, then we have the nozzle, and in the nozzle we have the spear. So we can control the amount of water entering the turbine with the help of spear. So if we move the spear forward, then that reduces the flow area, which in turn reduces the amount of water entering the turbine. And if we move the spear backwards, then that increases the flow area, which in turn increases the amount of water entering the turbine. So depending on our power requirement and depending on the load, we can increase or reduce the amount of water. As the load on the generator increases, that increases the load on the turbine wheel. So that reduces the speed if you don't provide more energy. So if you don't provide more energy, the increased load on the turbine reduces the speed of the turbine. But for power production, we need to maintain a constant speed. So for that purpose, what we do is we move the spear backward. So when we move that backward, the amount of water falling on the turbine or amount of water coming out of the nozzle increases, and we can maintain a constant speed whatever may be the load. So for that purpose, to have a fine control over the amount of water entering the turbine, we have the spear. And water enters this nozzle through the penstock. So penstock, as I had spoken earlier, it is the pipe connecting the dam and the turbine. So penstock will be present for all kinds of turbine, and the size of the penstock depends on the amount of water available. So here we know that Pelton wheel is a low discharge turbine. So here the size of the penstock may be smaller when compared to Francis or Kaplan turbine. So here we have the dam. So this is the level of dam when water is not being consumed, and here we have the tail race. So in this case, since we are dealing with a impulse turbine, only the pressure energy, all the pressure energy gets converted into kinetic energy in the nozzle, and only the kinetic energy will be absorbed by the runner or the blades. So because of that, here we don't worry about the level at which we keep the tailstock because we don't have a draft tube to maintain low pressure at the end of the turbine. In the case of a reaction turbine, both kinetic and pressure energy will be utilized, and because of that we need to have a proper draft tube. We need to have a proper casing and a draft tube. For an impulse turbine, we don't need a casing. The casing is provided here only to avoid the splashing of water in all direction and to keep the place dry. So because of that purpose we have the casing here, otherwise casing is not at all necessary for an impulse turbine. If it is a reaction turbine, then casing is an integral part of the turbine. For an impulse turbine, we don't need casing, but here we are providing casing, one thing to avoid splashing of water in all direction, and since the turbine is rotating at high speed, we need to keep the workers safe. So for that purpose we will provide a casing here. So now in the case of an impulse turbine, the gross head will be the head difference between the height difference between the head race water level and the nozzle. That is the amount of energy which we are going to utilize. Okay, so that is the gross head, and if you remove the frictional losses, then we will have the net head or the effective head which we can utilize to produce electrical energy, or that is the amount of energy that can be converted into mechanical energy by a turbine. Okay, so this is the net head or gross head, and we have the head loss due to friction. That is, as the water passes through the penstock, there will be friction between the water and the inner surface of the penstock, and that creates, and there will be fluid friction. So there will be friction between different layers of fluid, and that results in certain amount of loss of energy, that is HF. So here the water from the dam passes through the penstock and enters the nozzle, where we have the spear to control the fine to have a fine adjustment over the amount of water entering the turbine. So near the dam itself, we will have a valve that controls amount of water entering the penstock, and then to have a fine control, we have the spear here. Then once the water strikes the blades of the turbine, or in this case the buckets of the turbine, then the water will just drop down, and then that will be sent back to the river through a channel. So this is the working. Now the Pelton wheel, it will be rotating at a very high speed, and if you want to control the speed, that is to increase the speed or reduce the speed depending on the load, we have a spear, and that with the help of spear we can easily control the amount of water entering the turbine, thereby controlling the speed of the turbine. But if you want to stop the turbine entirely, since they will be rotating at very high speed, if you just stop the water flow here, then it takes very long duration to bring the Pelton wheel to rest. So instead of that, what we do is we have braking nozzles which supplies water in the opposite direction. So now the water is being supplied in this direction, so the turbine is rotating in anti-clockwise direction. So what we do is, somewhere here we will keep another jet, which when a load or when water passes through the nozzle, so that strikes the back of the bucket, and that helps in bringing the turbine to a standstill in a very short duration of time. So those kind of jet, we call it as braking jet. So braking jets will be provided in a very large scale Pelton wheel, where you need for some maintenance purpose, or if some accident happens, then you have to bring the turbine back to rest in a very short duration of time. For that we will use braking jets, and that supplies water in the opposite direction to that of the regular water jet. So that brings the Pelton wheel to rest. And then we have one nozzle and one jet, but if the amount of water available is more, or the power requirement from the turbine is more, or the size of the turbine is very large, then we can have multiple jets. So we have one jet here which is placed tangential at the bottom, then we can have one more jet here which will be tangential at some other point to the runner wheel. But all the jets, all the nozzles should be kept in such a way that they will be always supplying water or jet of water tangential to the runner of the turbine. So we can have 2 jets, we can have 3 jets, we can have 4 jets, depending on the power requirement, size of the turbine, and the amount of energy that needs to be produced. This is the working of the Pelton wheel. Now let us see the velocity triangle in the case of a Pelton wheel, and then we will see how to determine the work done.